Good morning and welcome to the 18th IEEE International Symposium on Embedded Multi-Core Many-Core Systems on Chip. The paper is called A Machine Learning-Based Decision Aid for Predictive Maintenance Using Fault Diagnosis Data by the researchers Mr. Saeed Al-Maqbali and myself, Asma Al-Marhoubi. When we talk about enhancing predictive maintenance with machine learning, there are several challenges which are available. One of these challenges is the growing importance of predictive maintenance. And this growing importance is becoming very crucial for Industry 4.0 because it reduces the downtime in general for the industry, for the industrial sector, and it minimizes the resource wastages, and it also increases the safety in general. There is also a need for decision support. Now, when we talk about the engineers do require data-driven insights to make timely and effective interventions when it comes to the manufacturing sector. There are some limitations which are available in the current method, which we have identified through our literature review. Many of these existing predictive maintenance approaches do suffer from some computational inefficiencies, or it can be also pure generalization, especially when it comes to multi-class and fault diagnosis. There's also a fourth challenge, which when it comes to the ineffectiveness of the traditional models which are available. Some of these models, for instance, the logistic regression, do struggle with nonlinear sensor data. On the other side, there are some complex models that could provide high performance, but at the same time, they have high computational costs. However, on the other side, there are some challenges which are available in the existing machine learning approaches. For instance, computational inefficiency and generalization. Now, many of the PDM's studies which are presented and mentioned in the research paper exhibit these issues, especially for the multi-class fault diagnosis. Another challenge is the limitation of the traditional models which are available. For instance, the logistic regression do struggle with non-linearities in some sensor data. High computational costs, complex models like SVM, we have the gradient boosting, we have the ANN, and the deep learning can be resources intensive and do require vast data and computing power. The last challenge is the narrow focus. Now, past research often concentrated on binary fault detection, overlooking the complexity of the real-world multi-class scenarios. Now, in ensemble learning and robust pipelines, ensemble method excel. Now, there are some algorithms like, for instance, random forest, XGBoost, which demonstrate superior accuracy, which is a very high accuracy rate, and robust and its robustness in PDM. They are often competitive with or outperform some of the deep learning on tabular sensor data. Some model choice is problem dependent, for instance, like random forests for stationary regimes, XBoost, and interactions. There are certain pipeline commitments which needs to be considered. One is the class imbalance management. Now, testing imbalance as a first-class design. Constraints like, for instance, such an example is the SMOTE with a training false. Time-sensitive validation, using the appropriate matrices, for instance, the precision recall, the over-accuracy, and validation strategies. Preprocessing and feature selection, they are essential for standardizing the data. for reducing the noise and selecting meaningful features to ensure the model generalization and interpretability. Our research question, balancing accuracy and speed, states the following. Which machine learning model provides the most effective decision aid in multi-class predictive maintenance task? Now, the approach that we have used was developed a simplified machine learning pipeline focused on real-time usability. We have compared ensemble-based machine learning algorithms like the random forest, XGBoost, and linear as well. We have considered the logistic regression classifiers. We have emphasized data imbalance management and feature selection. The ML pipeline that was used from data to decision. You see that we have mentioned the pre-processing, the feature selection, the class balancing, model training, and evaluation. So when it comes to cleaning, columns that were not informative, for instance, the timestamps, they were dropped. Encoding, fault classes were encoded by the method of label encoder. And when it came to the selection of feature, select K-best by use of ANOVA. The F-test was used to select the best 15 features which were available. In class balancing, the imbalance was solved by the synthetic minority oversampling technique, SMOTE, train test split, and the data was scattered 80-20 training testing. Three classifiers have been tested, which was the logistic regression, one versus rest strategies with linear baseline, and for random forest ensemble model of 100 trees. For XGBoost, gradient boosting made to be multi-class. And for the evaluation, the models were compared in terms of the accuracy and the F1 score, precision, recall, and AUC as well. The discriminative performance was plotted in ROC curve. The graph presents the industrial data analysis framework. The design of the methodology was structured into a machine learning pipeline, which was developed in Python with the help of Pandas, scikit-learn, imbalance-learn, and XGBoost. A stratified five-fold scheme was used as cross-validation, and the use of SMOT was confined as well to each training fold, which meant that the evaluation was not basis. Random forest took around 100 estimators and a maximum depth of 10, whereas XGBoost took a learning rate of 0.1 and 300 estimators. When it came to logistic regression, the logistic regression was based on the L2 regulations penalty, which is C equal to 100 as the baseline. The data set included 5 years of industrial sensor data, starting from January 2029 all the way to January 2024, which included operational parameters, environmental and machine health indicators, fault diagnosis, which is a multi-class encoded variable, was the target variable. The collected data set is available, and the reference is going to be provided in the paper itself. So the results of the model performance, we have compared, as mentioned earlier, between random forest, G-boost, and logistic regression. So when it comes to the accuracy, the random forest shows the highest accuracy of 0.864, and shows also the highest when it comes to F1 score, precision, recall, and AUC as well. And the graph below, which is the ROC curve, presents the results as well. So from the findings from the algorithms that has been applied, random forest shows an outperforming that it is outperforming the rest of the models. It has achieved the highest accuracy, as I have been stated earlier, of 86.4%, and AOC of 0.96 for multi-class fault diagnosis. XBoost, on the other hand, showed moderate accuracy of 62% with AOC 0.87. Logistic regression have provided poor performance with an accuracy of 22.4% with an AUC of 0.532%. Now, decision aid suitability, ensemble-based model, particularly the random forest, are highly suitable for predictive maintenance decision support due to their balance of accuracy and their computational efficiency as well, as it has been presented in the results. Now, in conclusion, effective machine learning for predictive maintenance. The machine learning specifically and interpretable pipeline utilization, the random forest is a highly effective decision aid for predictive maintenance. The high accuracy and in terms of high accuracy and efficiency, the pipeline achieved high multi-class fault diagnosis accuracy of 0.96 and computational efficiency, making it viable for real-time industrial systems. The value for ensemble methods. The study reinforces the superiority of ensemble techniques for complex multi-class fault detection in industrial environments, especially when it comes to balancing accuracy and speed. Study's uniqueness emphasizes the importance of pre-processing techniques like SMOTE and feature selection for generalizable models, which are often overlooked. The recommended future work that we came up with is the possibility of hybrid deep ensemble architecture, which enables or provides an opportunity to explore combining deep learning with ensemble methods for enhancing the performance. Explanation of future importance, future research into understanding which feature drive model decisions can be there. Retraining on online data, develop models that can lead to develop models that can learn and adapt over time through continuous retraining with new data. Real-time data stream integration, implement solutions that handle and process real-time data for immediate insights. The last point is the hybrid AI approaches, which investigates advanced hybrid AI strategies for improved predictive accuracy and adaptability in maintenance system. Thank you very much for attending the presentation.